Hello friends, welcome to this very first session on network analysis. Here we will be discussing some of the very basic concepts of network analysis starting from resistance. First topic we have chosen so that we can get in touch with one of the most important element of network analysis, which is resistance. So friends, the flow of electrons in any conductor causes the flow of current, and passage of electrons through a material is not accomplished without collisions of electrons with other atomic particles. Moreover, these collisions are not elastic and energy is lost in each collision. This loss in energy per unit charge is interpreted as a drop in potential across the material. This is the potential drop, and Ohm's law states that current in any conductor is directly proportional to the voltage applied across it. That's why we can write that V is proportional to I, or we can write that V is equal to IR if we remove this proportional symbol, and here the R is the proportionality constant, and R is equal to rho into L by A. So now this rho is a new term for you. It is a Greek alphabet, and rho is the resistivity of the material. It has nothing to do with the shape and size of the wire. It is the characteristic of the material. So very important to note that it is the characteristic of a material. It does not change with shape and size. And here you can also see that this rho is equal to R into, if we can measure the resistance of a particular size of that material, into A upon L, R into A upon L. So that's why what is the unit of rho, it also becomes important. So this unit of resistance, we know that the unit of resistance is ohm. It comes from same Ohm's law, and it is represented like this into unit of area is meter square if we look into MKS system, and unit of length is in meters. This square gets cancelled with this 1 m, and unit of resistivity becomes ohm meter. Ohm meter. Unit of resistivity becomes ohm meter. Okay, so L is the here the length of the conductor, and A is the area of cross section of this conductor. Now if we want to understand it better, then we can take one example. If a wire with resistance as 1 ohm is cut from center, and the resistance of half piece, if it is cut from center and the resistance of half piece of wire is to be calculated, then we can utilize the same formula, which is R is equal to rho into L upon A. What will come out to be the resistance? Now what has been the changes, we write here the resistivity, as you all know, remains the same. It is the characteristic of the material. L new length upon new area of cross section, LS. So resistance half wire becomes resistivity remains the same, the new length becomes half, so it is L by 2, and area of cross section remains the same. So we can note that the new R of half length becomes R by 2, resistance becomes half. So this way we can get a better clarity on resistivity. Moving ahead, if a wire with resistance as 1 ohm is stretched to double the length, if it is stretched and the length becomes double, what is the equivalent resistance? This question will provide you better clarity on the concept of resistivity, and the same formula will be utilized here, that resistance is equal to rho into L upon A. So now again friends, that this resistivity remains the same, and now we can see this resistivity new resistance, new resistance we have to calculate. So the rho remains the same, the length becomes double, length has doubled, and area of cross section when this length doubles, because the material is to be compensated, that is why the cross section area becomes half, and the new resistance becomes this 2 will come in the numerator and 4 into rho into L upon A. So this rho into L upon A is, we know that it is the R. So 4 into R. This new resistance becomes 4 into previous resistance, that was R. Okay, so friends, if we stretch a 1 ohm resistance to double the length, area of cross section will become the half and the resistance will become 4 times. Area of cross section is inversely proportional to resistance, and length is directly proportional to resistance. Now if we take one configuration of resistance, how we can arrange the resistance in the series configuration, this is the method how we can arrange 4 resistance in series configuration. Here there is a voltage source, DC voltage source, and 4 resistances have been connected in parallel. In series configuration, the voltage drop across each resistance is proportional to the value of resistance in ohms. Also, total voltage drop across all resistances when added together works out to be the voltage applied to the circuit. In this case it is V. So if here is the voltage V1, here it is the voltage drop of V2, here there is a voltage drop of V3, and here it is a voltage drop of V4, then V will be equal to, it will be equal to V1 plus V2 plus V3 plus V4, and this V1 will be proportional to R1. Voltage drop is always proportional to resistance, so V1 will be proportional to R1, V2 will be proportional to R2. More the resistance, more will be the voltage drop. V3 will be proportional to R3 and V4 will be proportional to R4. Okay friends, so now let us see the representation of this series configuration. In this image we can see what is the representation of this series configuration. Here 4 resistances are connected in series and they are represented like this. Here is the voltage source, and here if we find out the equivalent resistance, then it comes out to be R1 plus R2 plus R3 plus R4. We have seen that V1 is equal to V1 plus V2 plus V3 plus V4. If V1 is here, this is V1, this is V2, this is V3, and this is V4. Now V is equal to I into R. This I which is flowing in the complete circuit is I. I will remain the same across the circuit. That's why V is equal to I into R, and V1 will be equal to I into R1. V2 will be equal to I into R2. V3 will be equal to I into R3, and V4 will be equal to I into I R4. Okay, so this I cancels out from everywhere, and from here comes the equation of equivalent resistance, which is R equivalent is equal to R1 plus R2 plus R3 plus R4. Okay, so this is the derivation. Now if we arrange these resistances into parallel configuration, this is shown in all the household appliances. If we see at our home, then they are connected in parallel configuration, but there it is, that is the AC source, and here it is a DC source. To study the resistances in a simple manner, we always take a DC source for study of network analysis. These are connected in parallel, and if we see the representation, now this is the representation, all the four resistances connected in parallel. These resistances can be anything from your fan, or from you can say your refrigerator. Here we have seen that we have connected four bulbs across the voltage source in parallel, and it is represented like this. Now in case of parallel configuration, the equivalent conductance is the summation of all the conductances. You might remember that in series configuration the equivalent resistance was summation of all the resistances. In parallel configuration, equivalent conductance is the summation of all the conductances. 1 upon R equivalent is the conductance, and G1 is also 1 upon R1. So if we see here, this 1 upon R1 is the G1 and 1 upon R2 is the G2. So with this equation we can find out that the parallel configuration equivalent resistance is given by this equation. Now two important derivations can be drawn out from this equation. If one resistance, two resistances are connected in parallel, then the equivalent resistance can be found out by this equation. And if we reduce it to a more simple equation, then it would come out to be 1 upon R equivalent is equal to R2 plus R1 upon this LCM R1 into R2. Now again R equivalent will become product of the two resistances upon summation of the two resistances. So you can always remember this simple formula for calculating the equivalent resistance of two resistances connected in parallel. Now we take one more example to take a better clarity on this. If a wire with a resistance of 1 ohm is cut from center and both the pieces are connected in parallel, what is the equivalent resistance of the combination? So in the previous example we have seen that if it is cut from center, then the resistance becomes half. So there was a wire, we cut it from center, now we have connected these two pieces in parallel. So now we need to find out what is the equivalent resistance of this configuration looking from A and from point B. So friends, this equivalent resistance is going to be equal to the two resistances of value R by 2 are connected in parallel. So from the previous equation we have that R by 2 in parallel to R by 2. So product of the two resistances, R square by 4, R equivalent would be equal to product of the two resistances upon summation of two resistances, that will become R. So from here this R cancels out from the square and equivalent resistance become R by 4. So if two resistances are connected in parallel, the equivalent resistance become half of that, and as we have taken only half the resistances and connected into parallel, that's why the resistance has become R by 4. Thanks friends for attending this session, and we will be keep continuing sending you these important sessions. Thank you. Please subscribe Technitude.